Hi, in this lectures, we are going to develop the formula to determine the bending stress that we discussed in the last lectures for a beam or a sub of symmetrical cross-section. Like what we did before for members subjected to other types of loading, we will develop the bending stress equation based on the understanding of the bending deformation. That said, let us see how a beam or a shaft deforms when it is subjected to a bending moment. Let's say here is the original undeformed shape of a beam. If it is subjected to a positive bending moment, here is how it will deform. In this case, we can see that the top fibers of the beam are contracted, meaning compression, and the bottom fibers are elongated or in tension. Since the top and bottom portion of the beam are continuous, there must be a location within the beam where the normal strain in the direction of the beam is zero. A collection of such locations forms a surface, which can be better seen in 3 dimensions. The following is some terminologies associated with this surface. Before that, let me use this figure to say that we will limit our study to the members subjected to bending moment in the plane of symmetry only, like the one shown on the screen. Now back to our discussion. First, the surface that we mentioned is called neutral surface. Second, the line of intersection between this surface with a cross-section of the member is called neutral axis. Third, as you will see later on, the neutral surface goes through the centroid of each cross-section. Now let us study in detail the deformation of a differential length element, say this one. Let us focus our attention on the following 2 line segments. One on neutral surface and the other having a distance y from the neutral surface. We can see that before deformation, the lengths of the 2 line segments are the same. Now let us see the deformation. Since segment dx is on the neutral surface, its length does not change. That is not the case for segment ds, which is contracted with a new length of ds prime. Let us zoom in a little bit so that we can see better. Let us plot and define some geometries of deformation. Put the undeformed shape next to it for convenience in our analysis. Now here is the equation to find the normal strain for line segment ds. As a convention, the upward direction is usually used as the positive direction of parameter y. That said, we can rewrite the equation to determine the normal strain for line segment ds. From here, we see the normal strain that we defined is a linear function of y, which can be found based on the normal strain at the top fiber of the beam. As you can see, lowercase letter c indicates the distance from the neutral surface to the top edge of the beam. Now, based on Hooke's law, we know that the bending stress is also a linear function of distance y. That relationship can be visualized as follows. This stress distribution tells us if we can find the bending stress at the top edge of the beam, we will be able to find the bending stress at any location on the cross-section. To find that stress, we should remember that all the bending stress on this diagram is an equivalent of the internal bending moment at the cross-section. That said, the following is the development of the Flexure formula. First of all, let us find the location of the neutral axis. For that, let us define differential area dA like this one. Based on the stress distribution on the previous slide, here will be the force that exists on the area. This force is calculated by this equation. Since the internal normal force at the cross-section is 0, the integral of this force over the entire cross-section must be 0. That means the first moment of area of the cross-section about the neutral axis has to be 0, and that means the neutral axis has to go through the centroid of the cross-section. Now let us apply the same idea for internal bending moment. The moment caused by the internal force dF on area dA is calculated by the following equation. If we integrate this moment over the entire area of the cross-section, the result should be the internal bending moment. Based on this, we can see the relationship between the bending stress at the top edge of the beam with the bending moment. In other words, here is the equation to find that bending stress, where capital letter I is the moment of inertia of the cross-section that we learned in statics. From that stress, we can find the bending stress at any location on the cross-section. As you can see, for that we need to know the parameter y for the location of interest. The two equations that we highlighted in red here are called Flexure formula. In the case where we need to find the maximum absolute bending stress on the cross-section, we should use the following equation, where y max representing the point located furthest away from the neutral axis. That's all for this lecture. Thank you and see you in the next one.